So in the last lecture, we took up a common source amplifier and we uh, found out the noise factor. It was pointed out that since common source amplifier does not offer real impedance, so it cannot be used as LNA as it is. So it must be modified so that we can have real impedance, and that too that can be made equal to 50 ohm. So today we will take up the first out of 4 LNAs that was pointed out in one of the previous classes, and we will try to find out the noise factor and then compare with the common source amplifier. But before we take up this LNA, we would like to see what are the possible ways in which the first drawback of common source amplifier can be addressed, namely how we can make its input impedance real. So here we have a common source amplifier. That means input is at a gate and source may be grounded or may be degenerated, and we know that output will be ultimately taken from drain. So we are not showing the entire circuitry. So here we found that looking into the gate, we will see JD in infinite if gate to source capacitor is neglected, and in that case or that scenario arises for omega much less than omega t. So we have seen that this scenario corresponds to equivalently saying that CGS is equal to 0, and in that case Z in is going to be infinite. So how to make Z in real and maybe finite? So for this scenario, that means for this case 1 where omega operating frequency is much less than omega t, there are two ways in which we can make Z in real. So the first way here, the first way of achieving real Z in would be that we simply terminate this gate with a resistor R1. So now here, this is the input port. So if you look in this scenario, then Z in will appear to be real. In fact, we will see that this will turn out to be equal to R1. And this is the resistively terminated LNA. So this is one of the ways in which one can achieve real input impedance. The second way in which we can achieve real input impedance is again use a resistor, but not this time between gate and source. So here we have connected R1 effectively between gate and source. But this time we are going to connect a resistor between gate and drain. And this we will be designating as RF. And we will continue to take output from here. Input will be here. And in this case also, Z in turns out to be real. And this we will derive later on. Then, of course, can be made equal to 50 ohm also. So here we have gate and drain. and a resistor connected between these two. So these are the two ways in which we can modify this common source amplifier into LNA with 50 ohm impedance, and this will be when operating frequency is low. However, if the operating frequency is large, that means it is not so small compared with uh, the threshold frequency. So now what we will have is, so this is the case, third case, when omega is not much less than omega t. That is, in this case, CGS is no longer equal to 0. It cannot be neglected so easily. So if this is the case, then what happens is that looking into this gate, what we will see or anyone will see is the gate to source capacitor. So in this case, Z in will turn out to be capacitive. That means now Z in is going to have imaginary part as well. So once we have imaginary part, we can never achieve a real impedance unless we cancel out or neutralize this imaginary part. And since this imaginary part is of capacitive nature, so we must use an inductor or something of inductive nature in the circuit somewhere so that it cancels out this imaginary part of the Z in. By using resistor, you will never be able to neutralize this. So we will see that there is a fortunately simple uh, modification to this common source. Here we can add an inductor between source and ground. And in this case, you can see that source is no longer connected to ground. So this configuration is called degenerated CS LNA. And since this degeneration has been carried out with the help of inductor, so this is called inductively degenerated LNA. And once we do this, this Z in, new Z in or degen case, we will see that it will turn out to be real. And then of course you can make it equal to 50 ohm by suitable choice of parameters. So these are the three ways in which one can modify a well-known common source amplifier into an LNA. And in all of these three cases, you can note that input is, of course, at the gate. So this is how those three single MOS LNAs were evolved. Now, when we have this scenario, that means operating frequency is very small compared with the threshold, then there is one more way in which one can achieve a real input impedance, and that leads to the fourth LNA configuration, and that is common gate. So in this case, instead of giving input at the gate, we give input at the source. And here we will see that when we can neglect CGS, that means when we can do this, this Z-in will turn out to be also real. And here, of course, we continue to take the output from the drain, and the gate will be now at certain DC voltage. So for this case one, there are three ways in which real input impedance can be achieved. Two out of them are common source, one is common gate. And this case two, which is amplifier number 3, is when gate to source capacitor cannot be neglected. Now we will take up the resistively terminated LNA and try to find out the input impedance and then finally the noise factor. So first we'll find out Z in of resistively terminated LNA. So this is the LNA we are talking about, R1 and RS, and here we have our source. Now I'm showing the complete circuit, almost complete, and this is where we'll be taking output. We are not showing the biasing network now because we are only going to talk about the input side. And this is the input reference plane, and we want to know this input impedance looking at this location. So what we will have to do is substitute this MOS by a small signal model. And from this previous discussion, you can know that whenever we are talking about resistively terminated case, so this automatically implies that we have this scenario, and which will allow us to make CGS is equal to 0. And what we are going to do, we are going to neglect the channel length modulation just to keep the analysis simple. So these are the condition 1, condition 2. Under these two conditions, we are going to find out Z in and the noise factor. So for finding out Z in, what we have to do is we have to take this amplifier, excite it by unknown source, find out Ix, and Z in is going to be Vx by Ix. So this is what we are going to do on the input side. So now for this amplifier, we have to draw the equivalent model. And then apply this equation 1 for finding out the Z in. So we now draw the model of the MOS. So this is the model of the MOS. So here we have gate, here we have drain, and here we have source, and source is grounded. And there is a resistor from gate to ground. And then we have a source on this side, but keep in mind that our input reference plane is here, so we need not include this RS and VS. We can remove that source and just include an unknown voltage source here and find out Ix. So that ratio is going to give rise to the input impedance. So here we see that since gate to source terminal is open because of CGS is equal to 0. So in this case, clearly the Vx by Ix is simply going to be R1. So this is our Z in. So here analysis is very straightforward. And so one can choose R1 is equal to RS. R1 is equal to RS and equal to 50 ohm to fulfill the requirement of LNA. Now we are going to find out what will be the noise factor. For finding out noise factor, we have to replace each of the components in the previous circuit, the LNA, by its equivalent noise model, thermal noise model, and then apply the formula for the noise factor. So here we will follow all those steps that we pointed out. So in the step 1, we find out the equivalent noise model, the LNA. So here we substitute each of the components by its noise model, thermal noise model, and we are going to consider only the thermal noise, and that too we will not consider the gate noise. So here if we see this circuit, then we see that there are three elements which will be actually producing the noise. So first is this source itself, RS. Second is this R1 resistor, which we have used for uh, achieving the real input impedance. And the third source of thermal noise is going to be the MOS. So there are going to be three noise sources in this model. So we are going to so here is our MOS, and this is the noise current source due to the channel noise. Then we have two resistors, R1 and RS. So RS and its corresponding noise source. And here we have R1 and corresponding noise source. So this is a complete noise source model of the LNA. Now we have to decide whether we want to use Norton model of this LNA or the Thevenin model of this LNA to find out the noise factor. Because recall that for the noise factor F, we will have total output noise power divided by noise output power due to RS. So note here that on the input side we have two noise sources due to RS and due to R1. But in the denominator we will include only the effect of RS. So we are going to use the Norton model. So we will find out the short circuited output current due to each of the noise sources. So what we have to do is find out this short circuited output current. So this current because of Vn, V1n and ID. So we are going to use basically superposition principle to find output current due to each of the sources. So this is the source number, noise source number 1. So for this case, our circuit will be like this. So we have removed VA1N. That means we have short circuited it, and then we have open circuited the drain noise current. And here we have output shorted. So this output current we will be calling as IUN. So we want to know what will be IUN. So we can see from the KCL at the drain, says that IUN is going to be GM and VGS is this voltage between gate and source. Source is grounded. So this VGS also becomes the voltage across R1. And voltage across R1 can be found out by analyzing this part of the circuit. So VGS is V1, R1 divided by R1 plus RS into Vn. So this is the output noise current due to RS. Similarly, now we find out the output shorted noise current due to R1, that is V1N. So in this case, we make RS noiseless in this way, and we retain R1, and it's a noise voltage source. And we continue to keep ID out, and we will be calling this as IUN. So here also we find that IU1N is equal to GM VGS. Now VGS is this voltage across R1 and V1N, or alternatively, this VGS is voltage across RS. So this is VGS. So VGS is RS divided by RS plus R1 into V1N. Now we have to find out the short circuited output voltage, current. Due to MOS. That means that is due to ID. So now we have this circuit to be solved. So there's only one noise source, that is a channel noise source in this circuit. So here we will call this as IOD. So here we see that the two ends, the one end is already connected to the drain and the other end is grounded. So actually there is a short circuit across this ID current source. So what happens is the entire ID will take this path because it has a zero impedance path in this loop. So it turns out that IOD will be equal to simply ID. So now we have all the three currents available to us. So in step 3, we find the total output shorted noise current. And this total output current is going to be sum of ION plus IO1N plus IOD. Now using this, we have to find out the output power. So this will allow us to find out the total output power. And what we are going to use is Thevenin model. That means we will be interpreting our LNA using this circuit. So sorry, Norton model. So this is so here we had already seen that output power is going to be proportional to this mean square of the output current, right? So what we have already found out here, this thing, other equation says this is 2, this is 3, this is 4 and 5. So we just need to find out the mean square of this total output current that we have found out, and that will give us the total output power. So in step 4, E is going to be proportional to IO mean square, and this is going to be proportional to ION plus IO1N plus IOD mean square. And in this case, note that all these three currents, they are uncorrelated. So the mean square of the sum will simply be the sum of the mean squares. So we are going to get this thing. So total output power is going to be proportional to this quantity. And output power due to RS is going to be proportional to IUN mean square. So we have now both the numerator and denominator available to us. So in this case, we can find out the noise factor. So total output power divided by total output power due to RS only. So this will turn out to be IUN mean square IU1 and mean square plus IUD mean square divided by IUN mean square. So same proportionality factor exists for the two powers here in 6 and in 7, and that factor will be decided by the load and the output resistance. So this F becomes 1 plus IU1N mean square plus IUD mean square divided by IUN mean square. Now we substitute each of these terms. So here we have 4 K T gamma. No, this is from R1. So this will be, sorry, we have to use from equation 2, from 2, 3, and 4. F is equal to 1 plus this is going to be GM RS plus R1 into V1 whole square plus ID mean square GM R1 RS plus R1 V n mean square. So this becomes 1 plus GM square RS by RS plus R1 whole square plus V1 mean square plus ID mean square divided by GM square R1 divided by RS plus R1's whole square Vn mean square. So here we get RS plus R1 whole square into V1 mean square divided by Vn mean square plus RS plus R1 whole square ID mean square divided by GM square Vn mean square. Now we will substitute these V1, Vn, ID in terms of their expression. So when we substitute each of the sources by their expression, this is what we get. 4kt R1 delta F divided by 4kt Rs delta F plus Rs plus R1 whole square. So there will be R1 also in the denominator. 4kt gamma GD0 delta F divided by Gm square 4kt Rs R1 whole square. So this becomes 1 plus Rs by R1. Everything else cancels out. And here what we get is 1 by R1 plus Rs whole square gamma GD0. Delta F is here also. Rs divided by Gn square. So this is what we will get when we carry out the complete derivation. So this is the noise factor for resistively terminated LNA. Now here we will be using for match condition. That means for R1 is equal to Rs. So in this case F becomes 1 plus 1 plus 4 by Rs gamma GD0 by Gm square. So this turns out to be 2 plus 4 gamma GD0 by Rs Gm square. So in this case, we see that the minimum noise factor is going to be equal to 2. That means noise factor, noise figure, that means in dB, it's a minimum value, which we will be calling NF, will be equal to 3 dB. So for resistively terminated, F is always going to be greater or equal to 2, and noise figure is always going to be greater or equal to 3 dB. So the drawback of this resistively terminated LNA is we will see when we find out the noise factor of the subsequent LNAs, we will see that this has the largest noise factor. And in this case, we saw that there is no frequency dependent term here, and that arose because CGS was neglected because of the low frequency. So we say that this is broadband. In fact, this will be true for the 3 LNAs that we talked about: resistively terminated, and feedback LNA, and the common gate LNA. They all three will have this feature. Now here we can just compare its noise figure with that of common source case. So for that case, we had found out that the noise factor was 1 plus gamma GD0 divided by GM square RS plus omega by omega T whole square gamma GD0 RS. So this is what we had found out for the common source. Now for this resistively terminated case, what we found was 1 plus 4 RS gamma GD0 by GM whole square. So you can say that here we have the same term appears here, but now we have a factor 4 here, and then we have a term 1. And this term, you can say, is going to be small because uh, omega will definitely be always smaller than omega t. So this is going to be small. And now you can see that in general, the noise factor of resistively terminated is going to be greater than that of a common source, pure common source. But of course, this is not usable because Zn is not real. Right. So this is the comparison with the common source. So here we started with the noise model of the two resistors in the form of voltage sources, but we could have started with the noise model in current source form. So in this case, we have current source due to RS, IN, then current source due to R1, and all these four are grounded. And here we have drain current source. So again, we have three sources, and because of each of these three sources, we have to find out this short circuited output current. And when we try to find out that due to IN, what we see is this is the circuit we have to solve. RS, R1, both in parallel. So in this case, you can see that VGS is equal to RS parallel R1 IN. So ION is going to be GM VGS is equal to GM RS parallel R1 IN. So this is the first current, and second IO1N will be GM into VGS. So VGS is going to be of this similar form: RS parallel R1 I1N. Now third, that due to the channel or the drain noise current, output noise current in this case will also turn out to be ID. So now we have to find out the total power, and that is going to be again proportional to the sum of the mean squares. And in this case, the noise factor will be 1 plus ION plus, sorry, IO1N, IOD, D is mean square divided by ION mean square. So here also we can carry out this exercise, and the noise factor will turn out to be same thing that we have already derived, that is 1 plus RS by R1 plus 1 by RS plus 1 by R1 whole square GD0 RS by GM square. So this model will be useful when we have more number of parallel components. So here we had only 2 components, so we were able to easily handle this circuit even with the voltage source model of resistors. However, just say out of curiosity or as an exercise, if you want to include the gate to source capacitor, but keep in mind that once you include gate to source capacitor, input impedance is no longer going to be 50 ohms. So this is no longer usable as LNA, but just as an exercise, if this is the circuit that we want to solve for the noise factor, then taking the current source model for R1 and RS will be better, because this will allow us to do the calculation more quickly. So whether we take the voltage source model for each of the components or the current source model will be actually determined by the number of components and their combination. And by the way, for this case, noise factor will turn out to be 1 plus RS by R1 plus. So here we will see that omega term will appear. So these are the already existing terms. Now we are going to get a term which arises because of CGS. So this is with CGS, but usable as LNA. This is just to illustrate that taking current sources for these 2 resistors for their noise contribution will be easier to handle. So this is about the resistively terminated LNA. Now in the next class, we will talk about the second possible modification of CS with for the 50 ohm input impedance that leads to feedback version of the LNA.